Welcome back to WAPSI. So we can start a new section called magnetostatics. Okay, so in this section we will discuss the magnetic field due to the moving charges and their properties. Okay, inside a coil, outside coil, inside the axis, and okay, we can discuss all kind of questions. And the first question is, a moving electron produces, okay, electrons means what? Charge. When the charge is at a stationary position, the electric field is a property of static, okay, electrostatic. So in here the moving electron, the electron is just moving with a velocity. That means a moving charge will produce what? Current. So a current can produce magnetic field around it. So moving charge can produce magnetic field as well as electric field. So both electric and magnetic field, option B is the correct answer. Okay. So moving to the second question. A coil having 9 turns, okay, n is equal to 9, okay, carrying a current produces magnetic field B1, okay, B1 produced by a coil having 9 turns, okay, at the center, okay. Now the coil is rewounded into 3 turns carrying the same current. That means the same wire is used. That means the length is not changing. That means the perimeter of the coil is not changing. Okay, so actually what is the equation for magnetic field and connecting current and number of turns n? I will write the equation. B is the magnetic field, which is equal to mu 0 n I by 2r, because the coil is in the shape of circle. Okay, that if there is only one circle, then we can write as mu 0 I by 2r. If there is n circle, then we have to multiply by n. So B is equal to mu 0 n I by 2r. Okay, so for B1, what is n? N is 9. Okay, so n is 9. And for B2, the same wire is rewounded. So what happens? The radius of the circle will change and n will change. What is the new n? New n is 3. So mu 0 3I by 2r2. Okay, first radius is r1 and the second radius is r2. Okay, so now we want to connect the r1 and r2. So the perimeter of the first circle is 2 pi r1. Okay, 2 pi r1 is just multiplied by 9. That is equal to 2 pi r2 multiplied by 3. Okay, so 9 r1 equal to 3 r2. So actually what we want to substitute, we can substitute for r2. So r2 is equal to 3 r1. So B2 is equal to mu 0 3I by 2 into R2 is what? 3 R1. So B1 by B2 is equal to mu 0 9I by 2R divided by mu 0 3I by 6R. Okay, just cross multiplying each time. Mu 0 9I by 2R into 6R by mu 0 3I. Okay, so 2 into 3 is 6 and we can cut the 6. So R and R will cut, mu 0 and mu 0 cut, and I cut. So B1 by B2 is equal to 9. So which option we have? Actually they are asked to find the value of B2. So B2 will equal to B1 by 9. Okay, so B2 is equal to B1 by 9 and option A is the correct answer. Okay, so we can move to the third question. The magnetic field at the center of a circular coil of radius r. Okay, the same type of question, but the strategy is different. R carrying current I is 64 times the magnetic field at the distance x on its axis. So okay, then we want to know the equation for the magnetic field at the center and at an x distance from the center through the axis, at a distance x on its axis from the center of the coil. So what is the equation for magnetic field at this position? What is the equation for the magnetic field at this position? We want to already derive it. Okay. Then the value of x is, so we want to calculate the x. So what are the equations at the center? Okay. The B center is mu 0 I by 2R, because there is only one coil. If there is two coil, then multiplied by 2. Okay. And what is the equation for the magnetic field at axis at distance x, which is equal to mu 0 I by 2 into r square divided by r square plus x square all raised to 1 by 2. Sorry, 3 by 2. Okay, so r, if x is equal to 0, r square all raised to 3 by 2 is r cube. R square by r cube is 1 by r. Okay, so the same equation. We get the same equation when we substitute x as 0. Okay, so they have a relation. 64 times the magnetic field at the distance x. So we want to multiply BA by 64, then equate with the BC. So that means BC is equal to 64 times BA. Okay, then substitute mu 0 I by 2R is equal to 64 multiplied by mu 0 I r square divided by 2 into r square plus x square all raised to 3 by 2. We can cut the mu 0, we can cut the I, mu 0 I, and yes, then rearrange. We can cut the 2 also. Okay, so r square plus x square all raised to 3 by 2 is equal to 64 times r cube. Okay, so taking 1 by 3 on 1 by 3 on the 1 by 3 power raised to 1 by 3 on the either side of the equation. So we can cut the cube powers 3. Okay, so in the left side we get r square plus x square all raised to 1 by 2, which is equal to what is the value of 64 raised to 64 raised to 1 by 3. We can put that there for the time being into r cube, into r. So next we want to take the square on the both side. So r square plus x square is equal to 64 raised to 2 by 3. Okay, 64 raised to 2 by 3 into r square. Okay, so in the left side we have an r square, in the right side we have an r square. So we can take both the terms to the same side. So x square is equal to some constant r square minus r square. So subtracting minus 1. Subtracting 1 from 64 raised to 2 by 3. So actually 6 into 6 is 36. 36 into 6 is a large number. 4 into 4 is a 4 into 5 cube is 125. So 4 cube is actually 16 into 4. 16 into 4, which is 40 and 24. So that is 64. Yes. So the cube root of 64 is 4 and the square is 16. So we get the value r square plus x square is equal to 4r square. So x square equal to 3r square. X square is equal to 3r square. Okay. So x square is equal to 3r square. So x is equal to r root 3. Okay, x is equal to r root 3. Which option is the correct option? Option B is the correct option. X is equal to r root 3. Okay, so we can move to the fourth question. The magnetic hysteresis is exhibited by magnetic material dash. Which magnetic material? We want to find which magnetic material is responsible for the hysteresis. So, do you know the loop of hysteresis? I will draw a graph. the material start magnetization. When we give a magnetic field, start to magnetize linearly and it will stop, okay, at a saturation level. Then demagnetize it. It will not lose all the magnetic property. It will not lose all the magnetic property when the value of the magnetic field which we are given by is getting 0. Okay, then it will not lose all the magnetic field. So we want to give an additional opposing magnetic field to make the magnetization to get 0. Okay, that is continuing and we have to go to back. Okay, so when we are giving the 0 magnetic field, it have a negative magnetization in that material. That means the material is trying to be hold a effect of magnetic field. Okay, so this will be end at this position. Okay, approximately this is the structure of a hysteresis loop. This loop is very important to you. Okay, so this loop is exhibited by which kind of object? Only paramagnetic, only diamagnetic, only ferromagnetic? Yes, only ferromagnetic. So option C is the correct one. Only ferromagnetic substance can exhibit this kind of loop. Okay, in dia and para, while removing the magnetic field, it loses the magnetic property. Okay, so we can move to the 5th question. Okay, magnetic susceptibility. 5th question is related to magnetic susceptibility of Mg at 300 Kelvin. The temperature is, we can note that T1 is 300 Kelvin. Okay, is magnetic susceptibility chi E is 1.2 into 10 raised to minus 5. Okay, so they are asked to find the magnetic susceptibility at the new temperature 200 Kelvin. Okay, so T2 is given 200 Kelvin. That means that temperature is decreasing. What happens to the susceptibility? What is the relation between susceptibility and the temperature? Which equation? And the susceptibility is inversely proportional to temperature. That means when temperature increases, susceptibility will decrease. When temperature decreases, susceptibility will increase. So that is the relation. Chi E is inversely proportional to the temperature. Okay, so chi 1 by chi 2 is equal to T2 by T1. Okay, so we want chi 2. The second susceptibility chi 2 is equal to T1 by T2 into chi 1. Okay, what is the value of chi 1? That is 1.2 into 10 raised to minus 1. 1.2 into 10 raised to minus 5 is multiplied by T1 is 300 by 200. 0 zeros can be cancelled and 1 point divided by 2 is 0.6. 0.6 into 3 is 1.8. 1.8 into 10 raised to minus 5 is the value. 1.8 into 10 raised to minus 5 is the option C is the correct answer. 1.8 into 10 raised to minus 5. Yes, minus 5. So we can move to the 6th question. In the figure, a conducting ring of certain resistance is falling towards a current carrying straight long conductor. So the conductor is carrying a current. What happens to a conductor if the conductor is carrying a current? A magnetic field will produce around the conductor. So if this is the conductor and this is the direction of the current, then the magnetic field is like this. Okay, a curling magnetic field will produce. This can be explained by the direction can be explained by the right hand thumb rule. Okay, right hand, the thumb is placing towards the current and the curling of my fingers will represent the direction of the magnetic field. So if the current is going towards the right, the magnetic field is like this. If we are looking from this side, it will be anti-clockwise direction. Okay, so if the current is going like this, the magnetic field will produced from the center point of the circle. Okay, the magnetic field will emerge from the center to us, from the screen to us, from, we can say, I will mark the into at this circle. Okay, so the induced magnetic field is from the center to us from the page. Okay, so the circle, the current carrying, the conductor, the metal conductor will try to oppose that magnetic field by generating a current inside the conductor. Okay, in all ways, the induced magnetic field is try to oppose the magnetic field which is produced by the current. Okay, so we can calculate the direction of the magnetic field. Direction of the magnetic field will be into the page. Okay, into the page. That means this kind of magnetic field can only diffuse the magnetic field given by the conductor. Okay, so I can mark the generator induced magnetic field is as into the page. So in the same scenario, we can take our hands and put our thumbs into the page and curl. Okay, now the thumb is holding directed towards the left. That means the direction of the current will be like this. Okay, so that means the curling hand will be like this. That means clockwise direction. So that's how we can find the direction of the current is clockwise. Okay, so which option is the correct? Induced electric current is 0. That is wrong. Induced electric current is anti-clockwise. Induced electric current is clockwise. Ring will come to rest. So option 1 and 4 can be neglected by reading the options, and in option B and C it is anti-clockwise and it is clockwise. So which option is correct? Option C is clockwise. Okay, so why? What is the main reason that the direction is not to be anti-clockwise? The magnetic field induced in the ring is trying to oppose the real magnetic field. Okay, that is the main concept in here. In every time the induced magnetic field try to oppose the already occurred magnetic field. That's how we can define the direction of the current by the induction. Okay, so we can move to the 7th question. Okay, an induced current of 2 ampere, so I is equal to 2 ampere, flows through a coil. The resistance of the coil is 10 ohm. Okay, so R is equal to 10 ohm. Okay, what is the change in magnetic flux associated with the coil in 1 millisecond? That means the change in time, there is change in time. We have to calculate change in flux in the change in time. The change in time delta T is 1 millisecond. That means 1 into 10 raised to minus 3 seconds. We have to calculate the change in flux. Magnetic flux associated. What is the change in magnetic flux? So we have to calculate the change in phi. Okay, and we have the equation epsilon is equal to d phi by dt. Okay, so what is E is the potential. That means EMF generated. EMF is current into resistance. 2 into 10 is 20. 20 is equal to d phi by, that means we can put as change in phi by change in time, which is equal to change in phi by change in time is 1 into 10 raised to minus 3. So change in phi is equal to 10 raised to minus 3 into 20, which is equal to 2 into 10 raised to minus 2. So the options is 2 into 10 raised to minus 2 Weber. The option B is our correct answer, and yes, we can move to the next question. Okay, a charged particle is subjected to acceleration in a cyclotron. Okay, what's the working principle of cyclotron? 2 D's are there. Magnetic field by producing by giving a electric field. Okay, electric current, and the frequency is fixed by the RFO, and the direction, polarity will change according to the direction of the electric field. Okay, that's how it is oscillated inside the D's. Okay, the charged particle undergoes increase in its speed, okay, inside d1 and d2, and the gap option B is only inside d2 and only inside d1 and okay, this is d1 and this is d2. That kind of options are truly wrong. Okay, only inside d1 and both the d1 and d2 are correct. Both the d1 and d2 are same. Okay, inside d1 and d2 and the gap is the one option, and only in the gap between d1 and d2. Which option is correct? Only in the gap between d1 and d2, because the electric field is acting and give a force. Force means what? F is equal to ma. That means the electric field is giving an acceleration between the time between these gaps. So acceleration is acting between this gap, so the velocity is increased. The charged particle undergoes increase in its speed, so acceleration is acting in the center part, so acceleration means rate of change of velocity, so velocity is increasing between the d's. Okay, see you later. Okay, bye.